Welcome back, guys. So in the previous video we saw about the configuration, how the work done would be affected due to the configuration of charges, what would be the total potential energy stored in the system. Now the same concept, there's a little bit modification, and this is the work done, the potential energy stored in a system when there is already an electric field present in an external field. So in this case the only difference would be that apart from whatever calculations we did, there would be an extra term which is the work done due to the already present field. So we'll see that, and one more topic we'll be covering, that is the dipole in an external field. So what would be the potential stored in the dipole? I have written down the timings. If you directly want to skip, you can do so. Okay, let's start with the topics now. Okay, so now let's look at potential energy in an external field. So last time it was free space, that is there was no external field, but this time let's say there is a field present. Let me just draw a box to indicate that there is a field present, and whatever we are doing from infinity is being brought into this box where there is a potential present, where there is a field present. So now what would be the work done? To assemble two charges Q1 and Q2 at a distance r apart. So now what's going to be the work done? In the previous case it was 1 by 4 pi epsilon naught into Q1 Q2 by R1 R. So in this case there's going to be an extra term. So let's see how that is. So we are first bringing in the potential Q1 into the field, and this time the work done is not going to be 0. The previous case there was no potential, there was no initial field, so that's why there was no opposition and work done was 0. But this time there is going to be a work done. So steps: first bringing Q1. What happens is work done is not equal to 0. So what is going to be the work done? The work done equals, we saw the formula for work done, which was charge times the potential. So we are bringing in Q1. So it's going to be Q1 times the potential, which is not provided in this case but is present. If it is a numerical, the potential will be given. So in this case we'll just keep it as V. So Q1 times, let's say this region is charged with a potential V. So Q1 V, this is the work done. So now step 2, bringing Q2. So now what's going to be the work done? I'll call this work done 1. So work done 2 is going to be, we saw the first simple case previously, which is the Q1 times V, but this time what's going to happen is there's going to be this term where you're bringing Q2 times V because there's a potential, plus the one we already discussed, which is 1 by 4 pi epsilon naught 1 by 4 pi epsilon naught Q1 by R into Q2. And this is a term we already know. This is V potential due to the first one times Q2 and potential due to the field times Q2. So everything here is same, except that we have each case we have a new term, which is the potential of the present field times the charge you're bringing. So the sum of both these work done is the total potential energy. So let me just erase off this part. Have total potential energy of the system equals Q1 times V plus Q2 times V plus 1 by 4 pi epsilon naught Q1 Q2 by R. This is the potential energy of the system. The concept is that you have to add up the work done, that's it. The only difference is that there's a new term to the work done due to the present field. So you have to be very careful about the question. So we have seen this, now you can do the same logic for 3 charges. Now there's going to be Q1V, Q2V, Q3V, then the same terms as before. That is 1 by 4 pi epsilon. So for 3 charges it's going to be, this is for 2 charges. For 3 charges it's going to be potential energy is equal to the work done to bring the first charge, the work done to bring the second charge, the work done to bring the third charge. These are the new terms. The remaining is going to be as the same. So 1 by 4 pi epsilon naught Q1 Q2 by R12 plus Q2 Q3 by R23 plus Q1 Q3 by R13. So that's it. These three are the new terms. So we are finished with this topic. Now let's look at potential due to a dipole in an external field. Pole. So this is the topic, potential energy in a dipole. So what we are going to do is, first let's draw the diagram. So we have a field and we have a dipole. Okay, and let's say this is at an angle theta. The forces are going to be, this is the negative side, so it's going to be in this direction and in this direction. We don't need anything else from the diagram. We just need to calculate the work done. So as you see, in all these cases, it's very common that you find the work done and that is equal to the potential. So let's see what's the work done. Work done in any case is the force times the displacement. But in this case, it's a rotating object. So you're going to substitute the analogues of whatever is over here. So what's the rotational analog of force? It's torque. So torque times what is the rotational analog of displacement? It's angle, theta. So this is the work done for any rotating object. Now we are going to calculate a small work done and then integrate, because we cannot assume it for the entire circle because it stops at a point. So let's calculate the small work done, dW, which is equal to torque times d theta. Now we have previously discussed in the first chapter what is the total torque acting on a dipole, and we found out it was P cross E, where P is the dipole moment, P cross E d theta, and P cross E is PE sin theta d theta. This is the small work done. Now we have to integrate it and we are done with the answer. So we don't need the diagram. I'll erase off the diagram. How do we integrate this now? So integral of dW is equal to the entire work done is equal to, from, let me just first write the terms, PE sin theta d theta, and we have to now integrate this from where to where. It depends on us where we want to choose the angle, but let's say theta 1 to theta 2, and I'll just show you representing in diagrammatically. Let's say this is theta 1 at initial position, and then it rotates like this and it comes to a position over here, and now it is at an angle of theta 2. So if you have to rotate it from this position to this position, how much would be the work done? So it's a general case of thetas, angles. Which one you want to choose is up to you after the result has been obtained. So how do you integrate this? Dipole moment and electric field is constant because it's a uniform electric field as always. So PE is brought outside. Integral theta 1 to theta 2 of sin theta d theta. What is integral of sin theta? So you can remember it in this way. Integration is just the reverse operation of differentiation, and you already know differentiation. So d by d theta of sin theta, you know it's supposed to give you cos theta, and d by d theta of cos theta is equal to minus sin theta. Now these two are the most common ones. So what you do is you integrate on both sides, so that integral and differential is going to cancel out. They are opposite terms. It's just a simple way of saying, but this is not how it actually works. So if you integrate on either side, this is going to cancel off the differential, and you are left with integral of cos theta is sin theta, and that is one of the cases. And again you're going to cancel this off, so you get integral of, why do you have to keep the minus sign here? So you bring it to the other side. Integral of sin theta is minus cos theta. So now let's apply that. Integral of sin theta is negative of cos theta. So PE, I'm bringing the minus outside, cos theta from theta 1 to theta 2. Applying the limits, the total work done is equal to minus PE cos theta 2 minus cos theta 1. This is the work done. This is the total work done stored in a potential when it is rotated about from an angle of theta 1 to an angle of theta 2. So keeping this in mind, let's consider some specific cases. That is, I'll erase this off and write this as the heading. Okay, so if this is the work done, let's consider the dipole was first initially at an angle of 90 degree with the electric field. That is in this way. If it was like this, and then you're rotating it about to any angle you want, that is, the condition we have applied is that theta 1 equals 90 degrees and theta 2 equals theta 2, whichever angle you need. So what is cos of 90? It's 0. So you get the work done equals minus PE cos theta. Let's keep this as theta for any general angle. And this is the most commonly used formula, where you always assume the first angle is always at 90 degree. If in a numerical they haven't specified what is the initial angle and they just said rotated about an angle of 30 degrees, you have to assume it was as an angle of 90 degree. That is this case. This is what you need to consider it as. So work done is equal to minus P dot E, any of these two. So this is the general formula. It's better to keep this in mind, and you can derive with any angles you require. And then if this is the case, you will get to this result. So this is it for today's video. And in the next video, we'll look about the electrostatics of conductors. That is the properties of conductors, some rules. We'll discuss that in the next video. Thank you.